All right, welcome back, scholars. I am going to finish chapter 9. So we'll go through the rest of chapter 9. We'll talk about effect size measures. We'll talk about Cohen's D, or the estimated Cohen's D. We'll also talk about um, the R square, and we'll talk about how to calculate those things. We'll also discuss the importance of confidence intervals, and that'll be the last thing we talk about for chapter 9. And then we'll move on to chapter 10 on tomorrow, okay? So what we'll do is I'll work through a couple of examples. I'll show you how to calculate a lot of what we're going to be talking about, the estimated Cohen's D, the R square, and the confidence interval, and then we'll move forward. And then we'll move into some of the meat of what we'll be doing for t-tests. But we did learn about the t distribution, we learned about the t statistic, we learned about how to find the critical region using the t distribution and the table that we were handed out and passed out on Monday. And you're going to use those things moving forward for the next two chapters. And so we'll talk about that in a little more detail. So chapter 9, chapter 10, and chapter 11 are all based around the t-test. And so we'll talk about that. We're going to use that same table. We're going to use the degrees of freedom, like we've learned about. We're going to use our either one-tailed or two-tailed test to locate our critical region, and we'll work through the hypothesis test like we've done in the past. Okay, let me go ahead and do a few things on my end, and then we'll get started. Okay, so what we will be doing for the foreseeable future is learning about the differences between one group and the next. Okay, so what we're going to be doing is we're going to look at a population before the treatment, and then after the treatment, we're going to look and see what happens after the treatment. Okay, the treatment should create a difference, and that's what we're going to be testing for. The t-test is going to be looking at testing the mean before and the mean after. And we're hoping that the treatment has some type of effect, specifically some type of significant effect that shows that the treatment had some effect on the population of the treated population. Okay, so with the t-test, what we remember, we do not know the population standard deviation. Okay, and so when you don't know the population standard deviation, and many times we do not have an idea of what the population standard deviation is, we may know the mean at times, but we do not always know the standard deviation. And so with that, we're going to use the t-test because we have to estimate that standard deviation. And so with a normal distribution, we are making the assumption that the information that we are given follows a normal distribution. However, the only difference is when we do not know the population standard deviation, we will use a t-test. Okay. When we do know the population standard deviation, then we were able to use a z-score. Okay. And so we did learn also that any sample that is less than 30, less than 30, we will use a t-test. Oftentimes, the smaller the sample size, the flatter the distribution gets for a t-test, and we've talked about that. The larger the sample size, the more the t-test or the t-distribution looks normal. So if I have anything greater than or equal to 30, then it's going to look approximately normal, and so we would be able to use the z-score or the z-test. Okay, so but in our case, when we're comparing the population and an unknown treatment, we're going to use the t-test. Okay. So again, the 4 steps that we talked about, you're going to state your null and your alternative hypotheses. You're going to select an alpha level, and like I talked about on Monday, oftentimes we're going to use an alpha level of 0.05 or 5%. Okay, that is kind of the rule of thumb, and we're oftentimes going to use it at two-tailed test, unless, and like we talked about, if we know the direction of the change, right, or rather either an increase or a decrease specifically, then we can use a one-tailed test, and that's when we would use an alpha level very differently and the one-tailed test very differently. Okay, once you have your alpha level, you know your your alternative and your null hypothesis, you're going to set your critical region. Okay, and so we learned that T distribution table, you're going to use the maybe the two-tail test. You're going to use the column for the two-tail test. You're going to look at the row for the degree of freedom. And again, degree of freedom is n minus 1. So if I had a n of 10, the degree of freedom for that sample would be 9 because we're doing 10 minus 1 equals 9. Okay. And so we would use that intersection of the degree of freedom and the column for the alpha level, and that would be our T distribution or our T test, T statistic. Once we get our T statistic or our T critical, then we're going to calculate our T test statistic, and then once we get that T statistic, then we'll be able to compare that to the actual critical region to see if it falls in the critical region. If it falls in the critical region, that we will reject the null hypothesis. If it does not fall in that critical or that shaded region, then we will fail to reject the null hypothesis. Okay, so that's just something that we know. All right. So given the information, I'm going to go through this problem really quickly. We went through it in class, and hopefully, we got it pretty good. Okay, so we're going to walk through this, and I'm going to kind of walk through how we would calculate everything and how it will flow. Okay, so I'm going to stop sharing my screen, and I'm going to do something really quickly, and let's do this. I'm going to share my content on my whiteboard, and let's make it happen. All right. So the example that we have, it says, Chang, Ashbeck, Duffy, and Seisler report that reading from a light-emitting e-reader before bedtime can significantly affect sleep and lower alertness the next morning. To test this finding, a researcher obtains a sample of n equals 9 volunteers who agree to read at least 15 minutes using an e-reader during the hour before sleeping, and then take a standardized cognitive alertness test the next morning. For the general population, scores on the test average a mean of 50. So we're going to do a mean of 50. That's for the population. Okay. And then it says, and it forms a normal distribution. For the sample of research participants, they had an average score of a mean of 46. Okay. So mean of 46. And then it says they have a sum of squares of 162. Okay, so what we're going to do is now we have to go through our steps. So our step one, we just set our null hypothesis and our alternative hypothesis. So our null hypothesis would be, it's going to be, excuse me, erase that. So my null hypothesis is going to be the mean for e-reader equals 50. Okay. H1 or the alternative hypothesis would be, be a little more neat here. E-read does not equal 50. Okay, so the null hypothesis says that there is no difference between those who read the ebook or the e-reader before bedtime in the regular population, and the alternative hypothesis shows that there will be a difference in those who read the e-read. And we're talking about the difference in the levels of alertness the next morning. So again, the mean for the population, it shows that there is a slight difference in alertness from those who read the e-reader versus those who did not. Okay, so what we're going to do is now we're going to do step one. Here's step two. This is step one. Now we got to do step two. Okay, so step two is this. We're going to find our critical region. So we know that our degree of freedom is going to be n minus 1, which equals 9 minus 1 equals 8. Okay. We know that my alpha level is 0.05 or 5%. And so if we go to our T distribution table, we would find that our T critical is going to be plus or minus 2.306. Okay. So again, you'll go to your t-distribution table. You're going to look for a two-tail test, 5%. Okay. Then you're going to go down to degree of freedom 8. And at that intersection, you're going to find 2.306, and that'll be your critical region. The next thing is step 3. So now we have our critical region. Now we're going to go into computing our T statistic. The first thing we're going to do is going to be 3A. It's going to be the first thing we do. Okay. 3A is we have to find our variance and then also find our standard deviation, right? But our variance and our standard deviation are found using the sum of squares. So to find our variance, we're going to get S squared, which is variance, sum of squares over n minus 1 equals sum of squares over degree of freedom. Okay. So now we know what we have, right? So our variance is going to be 162 over 8 equals 20.25. Okay. If I wanted to go a step further and get my standard deviation, then I could. That would just be the square root of that. And so you just take the square root. I'm gonna do that really quickly on my calculator. So 20.25 square root. So S equals 4.5. Okay. And that's a really terrible 4. So we're going to do 4.5. All right. So now we have our standard deviation or our variance. And so the next step would be B, right? That's going to be the next step. I have to find my estimated standard error. And again, remember what we did on Monday. Okay. So my estimated standard error is going to look something like this. It's going to be the square root of S squared over N, which is going to be 1/6 would be 20.25 over 9. Okay. That's going to give me a square root of 2.25, which is going to give me 1.5. Okay. So that is the big difference there. Okay. That's the big difference. So now the final thing for step 3, we're going to label this C, is we're going to compute the T statistic. So the T statistic is T equals M minus the mean of the population over the estimated standard error, which then would give me, I know my mean is 46 for the sample, the population mean is 50 over 150, 1.5 equals, okay, that's going to be 4 or negative 4 over 1.50 equals a negative 2.67. Okay. So given the information, now I can calculate my step 4. Okay. So now I need to make a decision. And when I'm making a decision, I'm going to compare this number with this number. Okay. And so since this number is less than my negative 2.360, that means I can reject the null hypothesis. Okay. I can reject the null hypothesis, meaning that the e-reader or reading the e-reader at least 15 minutes before bed, during at least an hour before going to sleep, it caused a difference in the cognitive alertness the next morning. Okay. So again, that is how you would calculate a T statistic or T test using the information that we've been given. Okay. All right. So if I were to draw this out for those who need to see it visually, this would be the shaded region. This would be the shaded region. This would be 2.306. This would be negative 2.306. That would be positive. Okay. And so my value right here of negative 2.67 would fall well into this critical region right there, right? It would fall into that critical region right there, okay? So we got an understanding that that's how that works, all right? All right, so let me go back to my slides and stop sharing, and then we'll come back to that, okay? All right, so that's the example, okay? That is my example, and that's where we are, okay? If you need to pause the video, you can, just to see all the information that was provided to us, okay? So again, we talked about those 4 steps. We went through those 4 steps, step 1, 2, 3, and 4. Again, here is the depiction of the t distribution that we use. We have an alpha level of 0.05, degree of freedom 8, and our t critical is the 2.306 plus or minus, right? And so anything in this region, you reject the null hypothesis. Anything that falls in this region, you would fail to reject the null hypothesis, okay? But in our particular case, we reject the null hypothesis, okay? Here are the 2 assumptions that we use for a t-test, okay? The values in the sample must consist of independent observations. That is going to be the same for any test that we do, any statistical test that we do. That's one of the universal uh, rules or assumptions that we make about our data. Okay. And the second thing is the population sampled must be normal, right? So when the sample size is relatively large, this assumption can be violated without affecting the validity of the hypothesis test. So when we increase the sample size for a t-test, we know that the t-distribution becomes more and more normal. Okay. And so again, we know that when we are doing a t-test, the population that the sample is coming from has to be normal so that we can use that t distribution to then create those proportions and find those t critical regions, okay? 2 things that will impact the variance, okay? Will impact the variance and will also impact the likelihood of you getting or rejecting your null hypothesis or failing to reject your null hypothesis. So the larger your sample size, the smaller your error, right? The smaller your error, the larger your t statistic, okay? And so the larger your t statistic, the greater the likelihood that you will obtain a significant treatment effect or reject the null hypothesis. When you have a really, really large variance, you create a large error, and that large error decreases your t statistic. And the lower your t statistic, or the closer that t statistic is to 0, it reduces your likelihood of rejecting the null hypothesis, right? So you want to have a larger sample size in order to increase your likelihood that you're going to find something that's significant. And when you don't, then you see a big difference in what you find for your results. Okay. So here's a learning check. It says when n is small, less than 30, the t distribution is blank. Okay. So I'll let you pause the video, but the answer for this one is that it is more flat, right? So B is flatter and more spread out than the normal distribution. As you increase the n, and the n becomes a little larger, then it becomes more and more identical to the shape of a normal distribution or a z distribution. So it would be more like A, okay, if you were to increase it above 30, okay? True or false? It says decide each of the following statements is true or false. It says by chance, 2 samples selected from the same population have the same sample size and the same mean, which is a mean of 83. That means they will also have the same t statistic. Okay. The second problem, it says compared to a z-score, a hypothesis test with a t statistic requires less information about the population. Okay. You can pause it. Okay. But the first one is false because by chance, you will likely never select the same or have a population that has the same mean and the same variability in the same one after the other, right? Your variances are going to differ from one population to the next, or one sample to the next, excuse me. And each sample, like we talked about, has a certain amount of error because the sample is not identical to the population. It is just a sample of the population, right? If I added up all those samples and divided them by the number of samples I had, then I would be able to approximate the population variance and the population standard deviation. But with the samples, again, they're all going to vary because there is error when I take a sample out of a population. The second one was true, right? The t-statistic does not require the population standard deviation, meaning it does not require as much information as the z-test does, right? The z-test requires that we have a population standard deviation so that we can find the standard error of the mean. And since we don't have a standard deviation for a t-statistic, then we're using the estimated standard error of the mean to calculate our t-statistic. Okay. So effect size. Okay. Effect size. So once we have found maybe that we have a statistically significant difference, no matter how big or small that difference is, you always want to report an effect size. Okay. Just like we used in the z-test for the Cohen's d, the hypothesis test only tells you that there is a treatment effect, right? It doesn't tell you the likely, it doesn't tell you the magnitude, right? It doesn't tell you the magnitude at all. So we want to know what that magnitude is. Therefore, like I said, when we, again, are printing results from a hypothesis test, you should always report an effect size because that shows you the magnitude of that difference. Because the sample size sometimes can create a false sense of significance, right? The Cohen's d does not use the effects of the sample size at all, and so it just uses the difference between the mean and the sample mean and the population mean, and that gives us a better idea of what that magnitude of that difference is as we standardize it with the standard deviation. Okay, and so we'll talk about how we calculate the effect size measures, the Cohen's d or estimated Cohen's d, and the R squared. Okay, so here is how we calculate the standard deviation, okay, or the estimated Cohen's d, excuse me. Okay, so the original equation included the population parameters, but since we don't know the standard deviation, we're using an estimate, and that's why they call it an estimated Cohen's d, because we are using the sample standard deviation to compute the effect size. All of the thresholds are the same, but again, we're going to be using a sample standard deviation to be able to conduct and compute the Cohen's d. And we're going to go through an example, and I'll show you how it's done. Okay, so here is an example, right, of what the distribution looks like for that e-reader example. All right, so the standard deviation for our example, and I'm gonna go back and show you, was 4.5. Okay, so that is one standard deviation from the mean. Okay, if we look at our mean from the population, right, if the null hypothesis is true, again, that's a mean of 50. And we see the sample mean is a mean of 46. And so that difference, already we can see that there's a pretty large effect size there because, again, it is almost one standard deviation difference between the mean of the sample and the mean of the population. And I'm going to show you how we calculate the Cohen's d, and it's going to show you approximately how we will be able to determine that Cohen's d. All right, so let me go ahead and stop sharing, and I'm going to show you how we will calculate the Cohen's d, or in our case, we call it the estimated Cohen's d. All right, so let me go back to my whiteboard. All right, so new whiteboard. Now we're going to be talking about Cohen's d. We talked about our estimated Cohen's d, and our estimated Cohen's d is going to look something like this. Estimated Cohen's d, and we just call it estimated d, equals the mean, sample mean, minus the population mean over standard deviation. Okay, as we recall, the variance from our example was 20.25. Okay, so if we were to take the square root of that, all you got to do is take the square root. So it'll be s equals s squared equals the square root of 20.25 equals 4.50. Okay, so again, that is my standard deviation. Once I know my standard deviation, then it's pretty simple. Cohen's d We're going to do estimated D. It's going to equal, again, my mean over S equals 46 minus 50 over 4.5 equals 0.89. Okay, so now that is my Cohen's D. If you can remember the thresholds, this is a really, really high effect size, really, really large effect size. And this 0.89 is essentially telling me that the difference between my mean and my sample mean is almost 1 standard deviation, right? It's telling me that it's a really, really large effect size and that e-reader has a really big significant difference and plays a really, really big treatment effect on those who read the ebook, right, or the e-reader before going to bed, right? So that's a really, really high effect size. And again, you can see that depicted in the chart that we just looked at, because again, the difference, the standard deviation is 4, okay, 4.5. 1 standard deviation is 4.5. And so we see my difference between the mean and the population mean being 4, right? So that's 46 minus 50 equals 4. And so with knowing that information, I can see that this score and that, we're looking at this one and this one, is almost 1 standard deviation above the mean, right? So again, that's a really, really large effect size, and we can understand that that is going to be and show the magnitude of that difference, okay? So that is Cohen's D. Okay, that is Cohen's D. Let me stop sharing, and then we'll go back to my slides. Okay. Again, that was Cohen's D. Let's share. Okay. All right. So again, here's an example. Here's an example. It says a sample of n equals 16 individuals is selected from a population with a mean of 40, and the treatment is administered to the individuals in the sample. And after treatment, the sample has a mean of 44. It says it has a variance of 16, and we're going to use a two-tailed test with a 5% significant or a 5% significance level to determine whether the treatment effect is significant and compute the Cohen's D to measure the size of the treatment effect. Okay, you should obtain T equals 4 with a it says with a degree of freedom of 15, which is large enough to reject the null hypothesis with the Cohen's D of 1. Okay, so all I'm going to do, I'm going to walk through this one really, really briefly. But again, it's really, really easy, really, really easy. And essentially what I'm going to do, I'm just going to go over the Cohen's D. You can do this example on your own, but you should obtain a t-test of 4. Again, you're going to have a degree of freedom of 15. Obviously, n equals 16. So n minus 1 gives me that degree of freedom of 15. And I'm just going to go over the Cohen's D so you get the opportunity to see that one more time. Okay. Let me share the whiteboard again. Matter of fact, let me go ahead and do it. Yeah, so let's do the Cohen's D. All right. So I know that I have a. I'm gonna get everything out. So n equals 16. We have mean of 40, population mean of 40. We have a sample mean of 44. We have a variance of 16. Okay, so that I already know that my standard deviation is going to be 4, right? Square root of 4, 16, give me 4. All right. So then I can go ahead and do my Cohen's D, right? Cohen's D is going to be, we're going to do estimated D equals 44 minus 40 over 4. over 4 gives me 1. Okay, so that's the example. That's the example that we got, right? Say I wanted to go ahead and solve it all the way out. Okay, so let me go get my information. I need to find my, so we're going to go, I know my critical region, my T critical. Just going to write that here. So I know that is a degree of freedom of 15. I know we have an alpha level of 0.05. Okay. And so what I'm going to do is I'm using a two-tailed test, degree of freedom of 15. So I'm going to go down to two-tailed test over to two-tailed test. I'm going to go down to 15. I'm going to meet that. And that should be, the T critical should be 2.131. 2.131. Okay. So that should be my T critical. That should be my T critical, 2.131, right? So let's go ahead and do it, right? We already know what we need. Again, we're going to get my critical region. I already got that. My null hypothesis is just going to be this. Let's do this. It's going to be mean equals 40. And then H1 is going to be mean does not equal 40. Okay, so I already know that. Let me go ahead and compute my T statistic. All right, let's go ahead and do that. So that's going to be we got my, we're going to use my estimated standard error. We're going to go 16 over 16 equals, that's going to be 4 over 4 gives me 1, right? So now that I have that, I got to do my T statistic now. It's going to be 44 minus 40 over 1, which is 4 over 1 gives me 4. I have a T statistic of 4. Okay, so again, I compare that to my critical, T critical. Again, I rejected no hypothesis, right? There's a significant difference between the treatment and the population. Okay. All right. So let me stop sharing this, and then we'll finish up with R squared. All right. So again, as we see, here's an alternative to Cohen's D. And so sometimes what's very useful is we want to explain the variance of the measure, right? So when we do a treatment, the treatment causes variance in the scores, right? Every time, right? So when I give a student a treatment, and the differences in those scores is really based on the treatment. That's what we hope, right? And so when we do the R square is giving me how much variance is explained by the treatment effect, right? So that percentage that we get, we're going to get a percentage. That percentage is giving me how much of that variance is being explained by the treatment effect. So if almost, so a lower small effect size is around 1%. A large, medium or moderate effect size is around 9 to 10%, and a large effect size is around 25%. Right. So anything greater than 25%, that is a really, really large effect size. 25% means 25% of the variance in the scores in that sample are can be explained by the treatment effect or by whatever the treatment is. Okay, so we're going to go through an example. In our example, and here is what we see. Okay, one of the first examples that we see on the original scores is A, right? So we have 10 scores, right? And here's the mean, but we see the deviation. These red lines there are the deviations from the mean. Okay, those are the deviations from the mean, and those vary based on this number of scores. The B is adjusted scores with the treatment effect removed. So in our example, we had a mean of 50 and a sample mean of 46, right? So that was a difference in score, and the difference in the scores of 4, right? So in the original example, right, these are what happens when the treatment effect is in effect, right? But when you remove that, all they did was they added 4 to every value or every score. They added 4 to it, and so that's why you see it more balanced in the bottom down here. Okay, so they added 4 to every score that was up here, right? So instead of the 39 being 39, now it turned to 43. The 44 turned to 45. The 43 turned to 47, so on and so forth, right? So they added 4 to each of them. They removed the variability in the scores by adding 4 to the to each score in the adjusted scores. Okay, so I'm going to show you how we calculate the R squared. Okay, so if we go back, let me stop sharing, and then we're going to do an example. Okay, so in our example, we had a t-test of a negative 2.67. Okay, if we remember that. Okay, let me go here. Let me share my screen. Okay, so in our original example, we had a t-test or t-statistic of t equals a negative 2.67. We found that our degree of freedom. We found out our degrees of freedom. We had an N of 9. We have a degree of freedom of 8. Okay, and so if we want to do the R squared, your R squared equation is going to be t squared over t squared plus degree of freedom, okay, which then will give me R squared. That's going to be negative 2.67 squared over negative 2.67 squared plus 8. Okay, that is going to give me 7.13 on the top plus 15.13 on the bottom equals 0.47. Okay, so that is 47%. So in our example, the e-reader treatment, right? So those who read the e-reader and those who participated in that experiment, 47% of the variability in the scores that we see is explained by that treatment, right? By giving those individuals those e-readers and then reading it at least 15 minutes, an hour before bed, those differences in the scores, almost 50% of the variance is explained by them reading that e-reader, right? And so that explains, because again, an R square of 0.01 is a small effect size. R square of 0.09 is a medium effect size. And R square of 0.25 is a large effect size, right? So again, with a 47% or 0.47, that is extremely large effect size, okay? Extremely large, very, very large, okay? All right, we're almost to the end here. Let's see what else we can do. All right, share my screen one more time. Okay. All right. So here's just a practice question. You can practice on these questions. Really, really important that you get a lot of practice in. If you read through it, if you have any questions, please give me a call, give me an email, right? But again, you're going to use this information that you've been provided. They give you your mean. They give you your sample size. They give you your sample mean. They also give you your standard deviation. So given all that information, all you need to determine is whether answering questions while studying produced significantly higher exam scores. And again, you want to work through those 4 steps, and then you want to compute the 2 different measurements of effect size. So you want to compute the Cohen's d using that formula, and you also want to use once you find your t-statistic, you also want to use your r squared and be able to compute those things, because I'm going to ask you to compute those things on the exam. Okay, I'm not going to spend a lot of time going through too many examples. The last thing we'll talk about is confidence interval. Okay, and the confidence interval is an alternative technique for describing effect size. So what happens when we use a confidence interval for estimating the population mean is we use our sample mean, and then we want to locate the population mean somewhere near that population or that sample mean, right? So based on the assumption, right, we know that the sample mean should be fairly close to and be able to approximate the population mean, right? And so we want to be able to estimate the population mean from the sample mean. And so we use an interval that defines how near based on the estimate of the standard error that we use, the estimated standard error that we've used, okay? And we learned how to do confidence interval a few chapters ago, and we'll do another example to show you what that estimated standard error does, what the t-statistic is going to do for you, and what you're going to use that for, okay? You want to be able to confidently estimate that the population mean should be located in an interval near the statistic that we have computed, okay? So if we're using and wanted to find the value for the mean, the population mean, that interval, then we're going to use the equation in this bottom equation right here. So we're going to use this as our confidence interval. Okay, so that's how we're going to construct our confidence interval. For purposes of the class, we're oftentimes going to use what we call a 95% confidence interval, right? And a 95% confidence interval is, again, that 5% significance level, right? And when we use that 2.306, again, depending on what our degree of freedom is, that is what the t statistic is going to be. We're going to oftentimes going to use a 95% confidence interval. So we're 95% confident that the interval that I produce, my population mean will be somewhere in that interval, right? Because I'm 95% confident that 95% of the t values or the t statistics are located in between those intervals, okay? So when you construct your confidence interval, right, in any t distribution, the values pile up around t equals 0, because t equals 0 is that mean. Just like for the z distribution, the z has a mean of 0, the t has a mean of 0, right? And so for any alpha level, we use that 1 minus alpha proportion, and that t values fall between plus or minus t for the appropriate degrees of freedom, right? So for example, with a degree of freedom of 8, 95% of the t values fall between plus or minus 2.306. Okay, so we got that value 2.306 by using the degree of freedom of 8, and we're using the two-tailed test, right? The two-tailed test for 5%. We go down and we find 2.306. Okay, therefore, we can be 95% confident that a sample mean corresponds to a t in this interval, right? And so that's how we're so certain, because we know that 95% of the t values, 95% of the scores are going to fall within this range, okay? So again, here's just a visual depiction of that, right? So this middle 95%, we know that 95% of the t values are going to fall within this distribution in this shaded region, right? So if we have any values, any samples that we randomly select, we're 95% sure that it will fall in this region, okay? So for any sample mean, right, with a estimated standard error you can pick any degree of confidence. You can pick an 80% degree, 90% degree, 95, 99%, right? You can pick, again, any of those confidence intervals. But what you're going to do is when you're looking at the confidence interval, you have to look at the 1 minus the alpha level, right? So for a 10 or 90%, if we're using a 90% confidence interval, so we pick 90% as a confidence interval, and I know my degree of freedom is 9, I got to go to 10%, right? Two-tailed, I find a two-tailed test for the 10%. I go down to 9 degrees of freedom, and your t-test or your t-statistic, I'm going to go to the back of the book just to confirm, but your t-statistic should show you that. So I go to t, 10%, two-tailed, go here, degree of freedom, then I'm going to go down to 15, or 9, excuse me, and 1.833, right? So we go down to 9, go across, 10%, two tails, and you should see a plus or minus 1.833, okay? And so I'm going to go over an example real quick to show you how that works with the examples that we've already used, and then we'll get out of here, okay? So let me see, let me go and show you an example real quick, and then I'll end it. All right. So again, remember my confidence interval. Okay, is mean equals the sample mean plus or minus the t times the estimated standard error. Okay. So for our example, we're using what we call a 95% confidence interval, right? So what is the 95% confidence interval? 95% confidence. So in our example, we had an n of 9. Now we have a degree of freedom of 8. So our T critical was plus or minus 2.306. Okay. We did find out that my standard error of the mean or estimated standard error was 1.50. And I know that my mean, right, my sample mean, excuse me, was 46. Okay. So I have all the information I need to get that confidence in, right? So we're going to go, erase that and go a little higher up. So we're going to go mean equals 46 plus, and I'm just adding in all the information I have, 306 times 1.50. And that's going to give me a mean of 46 plus or minus 3.459. And then if we were to solve that out, that's going to give me, I'm going to put it in brackets. So it's going to be, the lower number is going to be 42.541. It's going to be 46 minus 3.459. And then it's going to be 49.459. Okay. So I'm 95% confident that my population mean will fall between 42.451 and 49.451. It's going to fall somewhere between those two values, right? I'm 95% confident in that, right? And so that's what a confidence interval means. I'm confident that my score, my population mean is going to fall somewhere in there. Okay. All right. Okay. So as I close up and wrap up, the desired confidence interval, right, or the desired confidence level, it either increases the width or decreases the width. Okay. So as I increase my confidence interval, right? So if I go from 95 to say 99% confidence, right? I'm going to increase, I'm going to increase my interval, my width of my interval increases, right? So when I want more confidence, so if I go from 99% confidence, I'm going to increase that interval, right? If I want to decrease my confidence, I'm going to decrease my interval, right? So when there's less confidence to be acceptable, the width of the interval decreases, right? So if I went from 95 to 90, then I'm going to decrease the width of my confidence interval, right? Sample size also plays a factor in the width of the interval, right? So if I have a larger sample, I have a smaller standard error of the mean, which is going to give me a smaller interval, right? If I have a smaller sample, it's going to give me a larger standard error, which would then give me a larger interval. So those are two ways or two factors that affect the width of the confidence interval, right? When we're reporting the results of a t-test, right, the first thing you're going to do is you're going to report whether you rejected the null hypothesis or not, right? Was the difference significant or non-significant, right? If it is significant, then you rejected the null hypothesis. If it's not significant, then you fail to reject the null hypothesis. And this is how you would identify, right? So T, you put in parentheses the degrees of freedom. So the n minus 1, 9 minus 1 is 8. You have your T statistic here, negative 2.67. You report the significance level, right? That would be um, point or P is less than 0.05, or you can do the exact probability, right? Which is P equals 29%, right? And that P equals 29% is that proportion, right? Is that proportion. So you go to um, negative 2.67 and you would look for that proportion to find that proportion in the table, okay? Um, Non-directional two-tailed test, we talked about that, right? This is the most commonly used. However, there are directional tests that could be used to, again, when there are situations where you know a direction of either increase or decrease in the score, you can use a two-tailed test. But most commonly, you're going to use you're going to use a two-tailed test instead of a one-tailed test. Okay. So here's an example of a one-tailed test with a degree of freedom of 8 and a alpha level of 0.05. And what you see is it increases the critical region. So that makes it a little easier and more likely that you're going to get a significant difference or reject the null hypothesis, right? With a two-tailed test, the value for a degree of freedom of 8 and a significance level of 0.05 was 2.306, right? But in this particular case, it's a negative point or 1.86. So again, so you're increasing the confidence interval, not the confidence, the critical region. So the likelihood increases that you'll have something significant. Okay. Here's just a learning check. It says the results of the hypothesis test are reported as follows. So you have T 21 equals 2.38. P is less than 0.05. So what was the statistical decision and how big was the sample? So if you read through them, you would select B. Okay, so the null hypothesis is rejected, right? Because it's P less than 0.05 and the sample N equals 22, because again, that's 21 is the degree of freedom. So the degree of freedom is in parentheses, so the actual number will be 22. Okay, true or false? The sample size has a great influence on the measures of effect size. That would be false. Okay. When the value of the t statistic is near 0, the null hypothesis should be rejected. That is false. Okay. Anything near 0, that means that you're not going to reject the null hypothesis. You're going to fail to reject the null hypothesis. Okay. And that's all I have. Okay. If you have any questions, if you have any concerns about anything, please email me. I have office hours on Tuesdays from 9 to 1, Wednesdays from 12 to 2, and then also on Thursdays from 9 to 1 virtually. So if you want to set up an appointment outside of any of those times, please let me know, and I'll be sure to accommodate you if I can. Okay. But I appreciate you joining in. Again, this is chapter 9. We'll start on chapter 10 moving forward, and we'll talk about the independent test, t-test, and then we'll move forward to repeated measures, t-test. Okay. So I hope you all have a good evening, and we'll see you all later.